one of the workshop organizers, Matus Telgarsky. He's going to talk about the approximation power of deep nets. And he's also going to provide his personal email address in case you want to send him any open problems for the afternoon open problem session, or if you have any personal problems you want to share with him.
You can also use the official one that I sent out earlier. So I'm hoping we can just kind of have fun in the afternoon when we have that session. We can just kind of point out that nothing's actually been solved and joke about how much work we have left to do. So, okay, so I'm going to talk about approximation power of deep networks. And this is an old topic. It's been kind of interwoven with the history of deep networks. And it's a fun topic. You can also take that to mean maybe that means the usefulness of it's in question. But it is a mathematically fun topic, and there are new uses of it that have come out. So, please ask questions and anything you want to know. I kind of took a random subset of what I know. So anything you want to know that's not in the slides, just feel free to ask. Somebody in the audience will know if it's not me. Okay, so let me just tell you, kind of in the most tedious way possible, exactly what I mean, and then we'll get back to the fun stuff. So just to nail it down, what I mean by the approximation power, just intuitively, we want to use deep networks for a lot of things. So we want to make sure that we haven't shot ourselves in the foot by trying to approximate something they can't. We want to, let's say, approximate the human brain. We got to make sure that it can do the same input-output mappings. So here's the formal specification of the problem. Oh, I'm just checking the phone. So we've got some function we think that nature is following, and we're going to replace with a neural network G. And our goal is that whatever the prediction problem was, we should be able to just stick in the neural net and do just as well. So just out of habit, I'm going to use the setting of statistical learning theory that you just heard Sasha talk about. So on the left, we have the true population risk. So I've written it as this pairwise loss function, the true population risk for some function f. And I want to do just as well with a deep network. Okay? For today's talk, this is the goal. We want these two quantities to be similar. It's good to stress this because a lot of people, when they state their approximation theorems, they're actually 50 miles downstream from this. And it's unclear whether what they proved implies this. But I think we can all agree this is a reasonable goal, at least in the setting of statistical learning theory. So we don't want to be talking about loss functions. We want to just be talking about f and g. So to make things simple, let's just say that L is Lipschitz in the first argument. Then we can get this upper bound. OK, so what do we know from this? Well, we can say two things. One is that these risks will be close if these things are close in this L1 distance. And the risk will also be close if these are close everywhere. OK? So a lot of people, when they talk about approximation power of deep networks, they talk about what they call universal approximation. And what that actually means that these are close everywhere, which implies that this is small, which implies that this is small. But I would actually say that this is the quantity we care about. So I'd be happy with proving this, but note that this p is given to you by nature. You don't have control over that p. You can't just say this is uniform or something that's convenient for you. OK, so that's just some terminology. People call these universal form approximation results. And if you look in the literature, people prove all sorts of different things. Yeah, there are all sorts of different problems. We're also interested in lower bounds. And lower bounds are much more dicey to pin down what we really want to be showing. So the lower bounds that I will show you today prove an L1 lower bound. That means that this is large in L1. So what that means, there's a large set with large probability mass such that the two differ. So that would imply that on that prediction problem, they don't do similarly. But you can look up a lot of papers where they actually use lower bounds. They do lower bounds in L infinity. But for today, this will be our gold standard. So we'll try to make this small, and we'll do it usually by making these close everywhere in this sense. And the lower bounds usually be L1, which is this integral. OK. And just to pin down some notation, I'll be talking about kind of the most standard boring version of a deep network. So it'll be this, this iterative sequence of these affine mappings and these coordinate-wise nonlinearities. I'm not going to talk about convolutional networks. I'm not going to talk about all sorts of fancy stuff. You can ask me about the fancy stuff if you want. A lot of these questions, it's easy to get loose answers, but to get tight answers is very hard. So even though you might tell me, oh, a convolutional network, that's actually a way of writing down a linear mapping with a lot of weight sharing. But actually, the form of a lot of these questions will differ if we work with convolutions directly. So please ask, don't be shy asking questions like, oh, is this still true for convolutions or something? OK, so let's get on with the fun. Oh, and let me also point out that I'll usually use the ReLU. And just for fun, I'm putting out there the this paper as the ReLU reference, thanks to Peter. Peter pointed out that this is the neocognitron paper, and it used 2 activation functions. One of them was the ReLU. So that's what I chose to cite for the ReLU. OK, so here's what we're going to talk about today. And again, feel free to interrupt. The slides will go online, so whatever we don't cover doesn't matter. You can check it later. So the first thing I want to tell all of you about are what I call elementary universal approximation. My goal is that everybody who comes in here for the first 20 minutes leaves and has an intuitive sense on why you can approximate continuous functions with deep networks. So usually when people talk about universal approximation, they cite some paper that exists. And if you open the paper, you see a bunch of Fourier analysis. So that's why I want to do this first section. For me, the first section is the most important. In the second section, I will review many of these classical theorems. There was basically just a whole swath of them that appeared between 89 and 93 or so. And they're really cool. A lot of them have different principles that guide them. A lot of them have different intuition you get about what deep networks can do and what they can't do, even if the theorem at the end looks the same. So that was the first 2 parts. They prove that we can approximate continuous functions, which, by the way, you might say to me, that's kind of to be honest, it's kind of a strange goal, right? Like, information theoretically, you need to work really hard to approximate continuous function in 2 dimensions. It's exponential in dimensions. So that's kind of a strange goal, but it's a sanity check. Then we'll look at more refined function families. And for these, we can actually show that there's a benefit of having more layers in a network. The first 2 parts will use shallow networks. The third one will not use shallow networks. The fourth one, I used this fancy term Sobolev space. Sobolev space basically just means that all the derivatives are bounded. What that means is that you can use Taylor approximations locally and do very well. So deep networks are very good at approximating these functions that have well-behaved local Taylor expansions. And then to close, I basically have like 8 slides, each of which could probably fill a talk. And we'll just see what we talk about. OK? But for me, actually, the most important is the first section. So I want everyone just to have kind of an intuitive sense that not only is it clear that deep network can fit anything, but it's also kind of fun coming up with these little gadgets, how to make them do it. It's like Legos. OK? It's good. People are in the right building and in the right city. We're in Berkeley. It's weather is nice. OK. 2019. OK. So let's start really simple. I want to approximate this with the neural network, and I'm going to use the step activation. Right? You're probably like, why am I in this room? Because you just plop down a bunch of these little things. OK? So what I've drawn here is the locations where I put them and the weight I put on them. So you might say, what was the point of this exercise? Actually, something already interesting has happened. So for those of you that are very familiar with polynomial approximation, polynomials cannot approximate flat regions. Okay? You have a function that's very flat and then has something complicated happen. The degree of that polynomial is going to be absurd. Okay? So why am I telling you this? I'm telling you this because you might use polynomials to explain deep networks or use vice versa or something, but you've already lost something. So already we have something interesting. The complexity of what we're describing here does not depend on the length of these flat regions, the volume of the regions. Okay? To represent this, I need 5 of these step functions. It doesn't matter how big that flat region is. Okay, let's do something more interesting. Let's do a curved function, still with step functions. So you might say, oh yeah, I know how to do this. I just kind of say I want to get epsilon close, I just sort of jot little marks. You do something like this. If you add those up, they kind of follow this stair-step pattern. And you can say, I understand this perfectly. You subdivide the range. It's a Lipschitz function. The number of steps I need is the Lipschitz constant divided by the epsilon. That's true. That's an upper bound. But it's very bad because it's paying the Lipschitz constant that's measured over here. It's paying it here. Okay? I mean, I'm just saying, like, you know, most people, they write their paper, they use this. But you're failing pretty badly over here. And actually, there's a very clean way to, there's an elementary way. Well, I don't know. I didn't learn this in elementary school. I learned this after elementary school. But the fundamental theorem of calculus, I can just write f of x. I can just write it in terms of these step functions. Okay? Now, why is this cool? You can interpret this as being an infinite collection of these step functions. I'm exactly getting f of x for all x. So this is a measure over ReLUs. And I'll show you at the end of the talk, I can sample from this thing. I can sample from this thing. So in other words, if you had me a univariate function, one of my favorite ways to approximate with a step function network is I write down its derivative, I sample from that, and that gives me my approximation. And I'll tell you how to get this. I'll tell you how to get exactly this at the end of the talk. And the cool thing about this is it depends on the actual gradient, so it's not paying for this flat region. Okay. See, it's already, see, this stuff is really fun. You know, I had never written this down before preparing this talk. Okay. So two interesting things have arisen already. One is that we have a nice average case estimate. It's not a worst case bound for the complexity of writing this with the step functions. Another thing is that we're using these infinite width networks. And for those of you that perhaps noticed we had 237 machine learning papers on arXiv yesterday, it has become very exciting for many people to use this infinite width formalism to study deep networks. So already in the univariate case, it arises in a cool way. Okay, let's keep going. Let's talk about ReLUs. So you can kind of see how this one's going to go too. Every time the slope changes. Now that's interesting. Before, when the function values changed, I did a step function. Now, when the slopes change. Okay, so now the complexity in terms of the ReLUs depends on changes in slope, which is like a second derivative thing, right? So indeed, if you do a similar equality to last time, this one's skipping some integration by parts steps, you get that you can write this as an infinite width neural network, now with the second derivative here. And I can, so if you give me a univariate function, I take its second derivative, I sample from it, I can get my ReLU. If that sounds too vague, I give you the sampling procedure at the end of the lecture. Okay, so this is cool because it's an average case estimate. And very quickly in this talk, we'll stop having average case estimates. Very quickly in this talk, we'll have lots of worst case things that are very loose. And I should say that there's a Colt paper from this year that studies this case. In fact, this might be in the paper. And in some sense, this is actually the optimal way of representing a univariate function with that's the point of that Colt paper. So it's whatever, in a couple weeks. Okay. That was univariate. All of you might be saying, come on, why univariate? Let's do multivariate, and just for fun, let's consider a finite point set. So for finite point set, we have a trick solution. The trick solution is sample random direction, the projections are unique, and I reduced it to a univariate problem. All of these things map to unique, they have unique projections, and so I can just solve a univariate problem now. So even if your goal was a finite point set, the representation could have really blown up badly if you do this. So this is actually not a good idea. And our goal was not to represent on finite point sets. Okay. So now let's go to the real case that we care about, which is we want to approximate multivariate functions with for now, shallow networks, essentially. Okay, so before, and I'm doing step functions for now. So before, when we had to approximate something, every time the range of the function changed, I just stuck one of my little bumps there. Okay? So the goal for now is that I want an indicator on the box. I want to be 1 inside the box, 0 outside. So you say, okay, I'll just do what I did before. I'll just add some supporting hyperplanes. But if you add these supporting hyperplanes and add them up, then you get this function. So all I've done is I've taken the 4 supporting hyperplanes and added them up. And so that gives me a function which is 4 inside here, which is the place where they all intersect, 3 in those other 4 regions, 2 in those other 4 regions. This is not what I wanted. I wanted to be 1 here and 0 elsewhere. Okay, so let everybody think for 20 seconds about various ways to fix this. And if I take too many of these 20 seconds, we'll run out of time, so we'll stop. So one thing you can do is you say, oh, I'll use another layer. I will subtract 3.5 from everything. So if I subtract 3.5 from everything, this is positive, everything else is negative, apply one more threshold, and now I've got the step I wanted. Okay? Cool. Now I have indicator on the square. And for those of you that like this sort of thing, let me just state a random sentence of analysis for you. Continuous functions can be uniformly approximated by indicators on boxes, so I can just add a bunch of these together and I'm done. But don't worry about that sentence if it didn't sound exciting for you. We have a funner proof than that. Also, we failed because we've used an extra layer. So I would like to do this with only one hidden layer. Okay, so the affine layer, the ReLU or the step layer, and then another affine layer. And I'll just tell you right now, interestingly enough, I do not know a direct one-layer construction for this. I've thought about it for over a couple of years now. I don't know how to do it. The only way I know how to do it is to hit it with some super heavyweight, overpowered hammer about approximating continuous functions. Oh, and yeah, this is not a continuous function. Just smooth it a little bit. Okay. So here's a cool way to solve this problem. It was rediscovered by one of my students, Bolton, who's in the audience, and it actually turns out it's in a paper from about 20 years ago. So here's a cool thing you can do. So our strategy for the cube was to add 4 supporting hyperplanes. Well, why stop at 4, right? Like my GPU has, like how much wattage does it burn? I'm not going to use only 4, so I'm just going to add every supporting hyperplane I can possibly think of. And this has a really cool property. If you think about this function, then notice that points very close to it, they are kind of they have a positive inner product with more of the step functions than points farther away. In fact, what you do is you draw this sort of cap, and the volume of this cap is the part you cannot see. So, long story short, we can actually construct something that's sort of morally like an indicator on a radial ball by just taking tons of supporting hyperplanes. Okay, so in my head, when I think, if somebody just, I walked home, well, I'm not going to tell you when I walked home last night. When I walked home on the street, I was prepared for somebody stopping me on the street, and if they asked me, how do you prove that deep networks approximate continuous functions, I would just say, man, just add enough hyperplanes. Now, let me say that something we'll get to in the later part of the story is that this construction actually seems to require 2 to the d nodes. If you use less than 2 to the d, then it's not close at all. One intuition for this is just the number of these spherical caps we have to approximate. But I have not written down a rigorous proof of this. It's just kind of in my head, so I won't promise it. Okay. Let me just say that from here, we can approximate continuous functions by a trick. So we take a regular continuous function, and what we do is we convolve it with this bump. If I normalize this bump to be a density, then Yeah, this is easier maybe if I just do it on the board, but I'll just read this one and we'll see how it goes. So here's the function I want to approximate. Here's it convolved with one of these bumps. And either by change of variable or properties of convolution, I can swap those two arguments. Equality. Equality, I stick the density over there, and now I push the absolute value inside. This thing is non-negative. And so look at what we're left with. We're left with this absolute value between x and something close to x, hopefully, times this probability density. So if P is highly concentrated, if it's highly concentrated at 0, then this thing will always be small. In particular, if you make this like a Gaussian, then we tune its variance to things related to the Lipschitz constant of this. OK, so what have I told you? What I've told you is that one way to approximate continuous functions with one-layer networks is you start by approximating a bump with tons of supporting hyperplanes. And then you take what you get and you convolve it with the function. And with a little argument and some tail inequalities on this, you can prove that you're epsilon close. Okay? Oh, and for people that want to check this in the literature, this is called a radial basis function. Okay, so for me, we'll get a couple other proofs in a couple minutes, but for me, this is the best I can do to show you an intuitive proof that we can approximate continuous functions. And here are two references. So at some point in the summer, we will hopefully put something online. But then you can look up right now this paper by Mascar and Michelli, which in '92, like I said, it was in that set of years where a lot of people worked on these things. They also proved a result like this. And they gave a size estimate. Their size estimate was roughly this. Okay, so exponential in dimension is the main thing to look out for. Okay. So what was the point of this section? So the point of this section in the univariate case was both to kind of get everybody just back from lunch break, or sorry, back from the coffee break, but also to point out that even in the univariate case, there's something pretty we can look at. Even in the univariate case, there was this thing where we can write things in terms of integrals, and oh look, there are these infinite width networks, and oh look, there are these complexity measures that are nice. Then I showed you that we can make these indicator atom boxes with 3 layers, and also these RBF convolution constructions with 2 layers. And I didn't mention it clearly, but if you do the math for how big the network needs to be, there's actually an extra factor d to the d here that I don't know if it's tight or not, but it seems pretty interesting. So just a couple of remarks from this section. So one is that all these constructions are very impractical. They pay, the size is huge, and the Lipschitz constant is going to scale like this, even if you're approximating a very well-behaved function. But a couple other interesting things happened. One is that some of the analysis was very different from polynomials because it was happy to deal with flat pieces. We also had this appearance of infinite width, and if you just want another quick calculation of another cool way to look at infinite width, is if we have the ReLU, and I want to approximate norms with the ReLU, then it's just this quick calculation. So personally, if you came to me 2 years ago and said, how hard is it to compute an L2 norm with a ReLU layer? I'd say it sounds really hard, but it's really this long. And another thing that'll typify everything else we talk about today is that we will not get as good complexity estimates as the ones we just covered. So we're not going to get these nice, from the univariate case, we're not going to get these nice average Lipschitz type bounds. We're going to get a lot of worst case bounds. Okay. Any questions? Just a little teaser, depending on how much time we have. Just 3 little questions if you want to puzzle yourself with them. We'll answer them at the end if we have time. Or you can just hunt me down. So question number 1 is, are a deep network, if I fix the architecture, is it closed under addition? So can I take 2 of these, add them together, and stay within the function class? Okay. That's question number 1. Question number 2, can I approximate Turing machines with RNNs? And question 3, everything I've been proving was an approximation result. I was approximating a continuous function with some network. Can I get an equality if I have a little bit of wiggle room, if I can make custom activations that are univariate? Equality. None of those proofs before would give us equalities. No way to do it. So can I get an equality here? So there's 3 little puzzles. We'll maybe answer them at the end. OK, so now I want to tell you about the classical universal approximation results, which, like I was saying earlier, are very pretty. Some of them might look a little intimidating, but in all the ones I looked at, I learned something interesting about deep networks just by going through the proof. So the first thing I want to point out is, what is the value of multiplication? So one of the proofs will heavily rely on polynomials. And just to show you that multiplication is interesting and gives us something interesting, so let's start with cosine, which is this outer red curve, and just raise it to the power. Okay? So if I could just multiply cosine by itself, I can get this really nice localized bump. And I've been kind of hinting to this whole talk that if I can do localized bumps, I can approximate continuous functions. So if I could just take powers of cosines, I claim that I could approximate any function I wanted. And indeed, here's a way to write it. So if I think about the indicator of this box as earlier, so I can write it as the product of these individual coordinate indicators. And I can also think about the product of the cosines along every direction. So if I look at this object here, it's just a bunch of these product for every dimension. So it's this nice localized bump. So if I had this, then I could approximate continuous functions in another way. And why is this interesting? Well, a lot of people some years back were heavily working on deep networks with multiplications just baked in. Probably in TensorFlow, you can just bake in all sorts of stuff and PyTorch. And so do you want to have a multiplication primitive in your network? If the networks we've defined so far can do this just fine, then maybe that hints that maybe you don't need that primitive. OK, so here's a trig identity that solves this problem. So we can convert products of cosines into just linear combinations of cosines. OK, so there's this little trig identity. I've just written 2 versions of it. But the point of this is I can take a product of cosines and convert it into a sum of cosines. Now that it's a sum of cosines, it's more like what we work with in a one-layer network. OK, so we'll use that in a second. Let me just remind you about something. Sort of the maybe most classical and maybe the result many people think about when they think about approximation theory is the theorem of Weierstrass in 1885 that says that polynomials can uniformly approximate continuous functions over compact sets. And let me just say that this is not an, I would say, obvious result. So, I mean, it's, I guess, acceptable to all of us, but it's not an obvious result. So for me, it's very easy to reason that polynomials can interpolate between points. You can just explicitly write down the interpolating polynomial, set the roots to something. And so you can write this down. But what's not clear is that the interpolating polynomial doesn't go crazy between the interpolation points. You might fix it to do some interpolation, and you might have some sort of cat and mouse game where you keep adding more interpolation points. It keeps getting crazier between them. So the fact that it's well behaved between the interpolation points is amazing. And that's why these proofs are cool. The proof that many people know, it's in the, why am I calling it the Erdős book? The Ellen Spencer probabilistic method book. They use the Bernstein proof because it's a cool application of Chebyshev's inequality. Weierstrass's original proof is works with analytic functions. You take a continuous function, you apply Gaussian smoothing, you get an analytic function, and in some sense there's some resemblance here, but it's also a cool proof. And some time ago, people made a beefed up version of all of these, which is called the Stone-Weierstrass theorem, which is that if I have any function family that behaves like polynomials, and the key thing for us right now is that it's closed under addition and multiplication. So it's a function class that's like polynomials. If I have f and g in the function class, f times g is also in the function class. Then I get the consequence of the Weierstrass theorem, which is that I can approximate continuous functions over compact sets. OK. So now we've reduced the goal of approximating continuous functions to just showing that we satisfy the conditions of this theorem. And there are more, actually, but the main one I want to highlight is we can do products. And like I was saying earlier, the fact that we can do products so easily with deep networks is cool. OK, so this is one of those classical uniform approximation proofs from 1989, Hornick-Stinchcomb-White. And the statement goes like this. It says, give me your activation function. And all I need is that, well, there should be continuity in there too. But all I need is that it goes to 0 on the left and 1 on the right. And be really squiggly in the middle. And now I define the function class of single nodes, single network nodes. If I look at linear combinations of these, which is what we're computing with affine, then the activation, then affine again, this thing uniformly approximates continuous function on complex sets. And we know from the previous slide that we can just reduce it to that Stone-Weierstrass theorem. We just have to show that we're closed under products. So how do we do that? Because, I mean, I don't know about all of you, but if you ask me if these things are closed under products, if I can just multiply together some ReLUs, it sounds pretty weird. So here are two ways to reduce this to the Stone-Weierstrass theorem. The first is the one that's in their proof. So using this trig identity I just showed you, I can work with this class, which is deep net or shallow networks with cosine activations. If I work with cosine activations, whenever I have two of these nodes multiplied together, I can use this identity to unravel it into a linear combination. Okay, so what have we shown? We've shown that we can approximate continuous functions if our activation function's cosine. That's not good enough. We want to use this arbitrary thing. But at this point, it's a univariate problem. And let me explain why. What I do is I take this thing. So I've got cosine of A transpose X plus B. And now all I have to do is approximate cosine very well with my other activation function. Because then I can just feed this in as a univariate input. So I've reduced it to a univariate problem. Now let me just say really quickly that when I read this proof, the Hornick proof, I was a little fuzzy on my trig identities. I felt kind of stupid reading it. And it was easier for me to use exponentiation. So you can go through the same proof. You can work with the function class of shallow networks with exponentiation activation, easily closed under products, and then use the same univariate argument. OK, so what we've shown, this is one of the classical results. It says that we can approximate continuous functions, and the proof method is to say, with special activations, I can do multiplication, and then I can approximate those activations with the activation you care about. So I thought this theorem was cool for many reasons, and one was that it heavily relies upon multiplication, which doesn't seem very comfortable when you're just working with ReLUs. OK, so that's one proof. Here are some comments. So this theorem seems to be for bounded activations, but you can get a ReLU result out of here by just plugging in this difference of ReLUs. And then you get a network that uses these things, and then you just expand it into a network with ReLUs. So this is a ReLU result. Another thing is that if you go through the proof and you do kind of incomplete bookkeeping on how big all the terms are, you do get this exponential blow up in dimension, and it seems actually that this omega is quite large. Here's another cool thing I'll tell you about more on the next slide. You might wonder what the best conditions on sigma are. So there's a very intense version of this theorem. It's actually stronger than this even. There are discontinuities allowed too. But the version I'll tell you now is that we're fine if and only if your activation's not a polynomial. OK, so for people that have not heard this result, maybe it's fun to think about it for a little bit before I tell you how it's proved. So it's kind of funny, right? Everybody loves polynomials, but now I'm telling you the last thing you should do with your deep network is use a polynomial activation. Of course, this is an idealized result, right? I have like infinitely, I have any budget I want of nodes. I'm not saying, in practice, maybe like x to the fourth is the best activation in history. I don't know. OK. OK, so here are some other theorems. Let me just do a time check to make sure I don't finish on like slide 5.
Question?
Yeah.
What is the lower bound for multiplication?
Oh, you mean you want a lower bound for how many nodes we need to approximate multiplication. This is actually super complicated. I will give you two answers right now, and we'll come back to it later. People are obviously obsessed with this because of how important multiplication is. The first thing I can tell you is that those earlier bounds I gave you oh, let me also tell everybody that here's just a little, here's a little trick that whenever I talk about multiplication, I'm going to talk about squaring by something called the polarization identity. And there are many ways to write this, but one way is okay. So I don't need, so because of this, if I can do squaring, I can do multiplication.
You have to be careful whether you're doing additive or multiplicative approximation here, right?
It actually, for this one, it works out. All the formal proofs about this. Okay, so to answer the question, everybody remembers earlier I had that average Lipschitz construction, and gloriously Nati has walked in. As I was saying, there's that theorem that says that these infinite width constructions are the minimum norm solutions. So you can use that to probably get some sort of lower bound for this shallow construction. Okay, so that's shallow constructions. Later, I'm going to tell you about deep constructions for multiplication. So deep constructions for multiplication is known that we could get additive epsilon with a network whose size is log 1 over epsilon, depth and width. You might say, great. The problem is that the Lipschitz constant of this network is actually 1 over epsilon. So let's be clear here. I'm approximating x squared, which is constant of 2 on 0, 1. Why is my Lipschitz constant going crazy? So this is unfortunate. Okay, but I know that was a very long answer for a short question. There is evidence, but it's very incomplete. Okay, so let me go through a bunch of these classical ones. Let me just do another time check. Okay, so I'll just tell you these in maybe 2 sentences. The one that most people talk about is this proof by George Sabenko, and it works as follows. It uses a high-powered version of orthogonality called the Hahn-Banach theorem, and it reduces the problem to saying that if I have some fancy signed measure, then this integral, so this inner product here, if you will, is 0 if and only if the measure is 0. So that's basically saying that if I have some measure and if it has any bumps, then I can always pick them out with these. And he uses Fourier analysis to prove that. Okay, then there's this proof I was telling you about that says that if and only if your activation is not a polynomial, you can approximate continuous functions. So let's do the negative direction first. If my activation is a polynomial, linear combinations of polynomial do not increase the degree. So if my activation has degree d, or r, sorry, if my activation has degree r, I can even approximate things that are degree r plus 1. Okay, so that's why if your activation function is a fixed degree polynomial, you're in trouble. The other direction is absolutely insane. The other direction, what it says is that suppose you're not a polynomial. It does a little bit of math and proves that you have infinitely many derivatives. It does not assume smoothness. And from infinitely many derivatives, it points out that you can do a bunch of clever math to basically get any monomial you want. And I'll just tell you one little trick from the proof. Notice that, okay, here's my activation. I'm going to work univariate right now. Here's an activation. Okay. Here's my activation. Here's just some univariate network, right? I'm going to subtract off this. That's a network. And I'm going to scale everything by 1 over tau. Does this look like anything to anybody? What if I take some limits? So you can, if you have a function in your neural net class, you can write its derivative in your neural net class. And using that, you can fancily get polynomials. Okay? If that doesn't sound, so I'm just trying to show you how cool this proof is. See, this is why I like a lot of these proofs. You read them and you find all this crazy stuff. Okay, then the Barron proof is extremely interesting. One way to look at the Barron proof is like this. The Barron proof that everyone talks about, but for many reasons, many people talk about the sampling procedure. The Barron proof is effectively using a complex exponential activation function. And if you use this complex exponential activation function, I can write any function I want as an infinite width network where the measure on my activation is given by the Fourier transform, by the inverse Fourier transform theorem. Right? Isn't this cool? This is so cool. So it's saying I can have my f of x, and I can write it like this. And to get his bounds, he takes the real part of this and then samples from this integral. So I knew about this paper for like 10 years. I was scared of the Fourier analysis. And all I knew about it was this Mori sampling thing, which is amazing. And 10 years later, I like checked some of the Fourier analysis, and it's amazing. OK, so that's cool. Another cool thing about this theorem is that you get an estimate that's not just 1 over L over epsilon to the d. So you actually get an estimate for how many nodes you need that can be a lot better. And I should also say that there's another paper by Funahashi that I've only skimmed. It's from the same era. It is not cited often, I think just due to coincidences. And it looks pretty intense. I was reading it last night, and I just saw a bunch of Fourier theorems I didn't know. So, OK, so I got kind of too excited, but you can see that on one hand, these are kind of lame theorems. You might say, oh, who cares about continuous functions? All the estimates are exponential. But for every one of them, you learn something cool about how to use networks and how to combine them and things like that. That's why I like these. OK, so just a few quick comments that we haven't done anything with depth. And we haven't even done anything with neural networks. A lot of these proofs, we could just change some words, and the same proof shows that boosting and RBF-SVM. So I mentioned it to everybody, this use of the exponential activation. Let me tell you how I thought of this. I was reading in Ingo Steinward's book the proof that SVMs with RBF activation can fit continuous functions. And I was reading and I thought, wait a minute. This is a neural net theorem. So, OK. Do you have any questions? 12:30, right? Any questions? Okay, I get too excited talking about this stuff. I haven't been able to talk about this stuff for years. It's so exciting. Okay. Aren't these cool? Like, OK. Now I want to talk about, OK, so far I've given you what I claimed originally was an intuitive explanation that we can approximate continuous functions, but ended up, I guess, not being that intuitive. The second part was I reviewed a bunch of these classical theorems. So far, everything has been shallow representation. The only hint I had of a non-shallow representation was when I used 3 layers to approximate the box function and saved a d to the d factor, maybe. OK, so now I will talk about a variety of results that use depth to show that there are nice things you can approximate a little bit of depth, a little bit of extra depth, and they have lower bounds with them. OK, so the first thing I want to tell you is that, actually, let me just do another time calculation. OK, so I will just tell you this slide in an impressionistic way. So all I'm telling you here is that radial functions are easy to approximate with 2 layers. One layer computes the squared norm, which you can just do coordinate-wise, and the other layer just approximates the function. The only reason I wrote out the calculation was because this hideous triangle inequality is actually what kills lots of deep network papers. So the paper that Dylan Foster, Peter Bartlett, and I wrote that has this spectral normalized bound, it has this exponential Lipschitz constant baked in. And it's because of a step like this. OK. So that's why I wrote that step out. These slides will be posted. You can check them later. The punchline is that 2 layers radial functions, or 2 ReLU layers radial functions, easy. OK. If we only have 1 ReLU layer, it's super not easy. So as I was hinting before, there exists, OK, let's just go through this slowly. So this is by Ronen Aldan and Ohad Shamir. So this result says that if there exists a radial function f, and it's a very complicated, randomly constructed radial function. So this is not an easy result to prove, or just imagine even. So there exists a radial function f, which if we have 2 ReLU layers, we can do just fine. We can get it really close with polynomial complexity. So there exists this function and a probability measure. So I've kind of missed a little on my original goal. I'm constructing a probability measure that'll make the lower bound a little better. OK, So there's a probability measure so that anything with only one ReLU layer and exponential size has a constant lower bound. So it's a constant away. This does not depend on dimension or anything else. This is really just some constant. And I should say that it's not, this proof is terrifically difficult, and it's been 4 years and it hasn't been redone actually. It hasn't, so just making this like the uniform measure or something hasn't been done. If you think there's another result, I think I know the other results. We'll just mention this. Okay, the proof is super intense. The proof says this is an L2 norm. I can just Fourier transform everything inside of it, and everything stays the same. And then if I look at the Fourier transforms, the two-layer thing, or the one-layer thing, I know exactly what that ReLU transform is, or this Fourier transform is. It's all these little tubes. And the other guy he's huge. The tubes can't cover it. I'm not going to say more about it. The proof is super intense. I was reviewing it again last night and finding more steps that I'd forgotten about. So it's a kind of a tour de force proof. If you want just a bunch of really intense Fourier transforms, if you like this guy named Bessel, then you should check this proof. Okay, so here is a very nice related result, not directly implying it, but very nice. So now we have two inputs. We'll just say they're both d-dimensional. They're uniformly distributed on the sphere. Okay? And now what I'm looking at is the sine function, oscillatory, of their product. And because of this, products and norms are related. I can just make this all norms. Okay, so this function h, this sine of this product, I can approximate let me say it this way. So if I have a single layer and my width is d to the d, then I can't get within a constant. And this is really the uniform measure now. This is great. The only thing that's weakened since last time is I have a bound on the weight magnitudes. The weight magnitudes have to be at most 2 to the d, which I don't know about you, but in my PyTorch code, I'm not getting up to 2 to the d on my ReLU weights. And we can approximate this really easily with 2 layers. Okay, so the main thing to think about the difference between these two is that this one sweats really hard and does not have the bound on the weights, and this one has the bound on the weights. Proofs are completely different. The proof of this one uses so this is by Amit Danieli, and it has this, he's very good with, I remember I wrote to him after he found this proof. I was like, how did you do this? He's like, yeah, I'm just good at orthogonal polynomials. So use orthogonal polynomials on the sphere that's called spherical harmonics, and you basically just use these lemmas that Amit knew, and you reduce it to a univariate problem. You're just comparing two functions on the line, and now it becomes a region counting argument that I'll show you in a second. So I really like this proof a lot. It's very clean, and the idea behind the proof is different. This is not merely a technical thing, this bound. It's actually internally a different proof. Or okay, maybe we can ask all three of them if it's, I think it's a very different proof, though. Okay, so do another time check, do another calibration. So let me give you my intuition on why this problem is hard. This intuition is not, I think, explicitly what makes the proofs work. And also, this intuition, as far as I know, has not been converted into a proof by anybody. So you can just take this as, my little bullseye drawing, if you will. But for me, this is my intuition on what's going on here. So let's say I want to approximate some radial function, and the radial function, the way I'm writing it is just this contour plot. So it's some value in this shell, some value in this shell, some other value on these different shells. If I could approximate these individual shells, I could just add them together and approximate the function. Okay, now here's the problem. If you try to approximate this thing with one of our little networks, here's what I'm going to do. I'm going to make the width of this 1 over d. If I make the width of this 1 over d, that shell has constant volume. And the problem now is this thing is so small that if you push your hyperplane very close to this inner ring, then you're going to need exponentially many of these. And if you push it any farther, you're going to catch a lot of the 0 and you're getting the wrong answer. So my intuition on what's going on in these proofs, again, this intuition has not been converted into a proof. My intuition is that you basically end up with these little thin shells, and you just need, there's basically exponentially many of these little caps you have to cover, related to the fact that there are exponentially many nearly orthogonal directions in high-dimensional Gaussians. Okay. So let me tell you one more result. So what we've discussed so far is that if we have one ReLU layer, we have trouble with radial or radial-like functions. And with two ReLU layers, we can do really well. The natural question is, what can I do with different numbers of layers? So for this, let's go back to the drawing board. So if we have a shallow representation, it's an addition of functions, a single layer or whatever, what are we bad at? So we're bad at many things, but one of the things we're bad at is, imagine if I have a very bumpy function. So at least in my head, whenever I have a very bumpy function, if I'm working with one of the usual kinds of bases we have, I have to kind of use another basis element for every one of these. That's just kind of what I have baked into my head, another support vector for each one or something. So let's try to build a function which gets bumpy as fast as possible and try to approximate with a shallow thing and see what happens. So here's a little observation. So this thing called the tent map from dynamical systems, I guess you can kind of tell it's blue and red. So I've colored 1/2 blue and 1/2 red. If I take some function and I apply it to the output, this is what happens. So this here is just going from 0 to 1, and this here just going to 0 to 1 backwards. So f of triangle of x, or f of tent map of x, is just 2 copies of f, the second one being reversed. Okay? So again, the way I do this in my head is I get 1 copy of the domain. In this composition, I get 1 copy of the domain, a second copy of the domain backwards. And so if you do the natural thing that people do when they like to break things, which is compose it with itself, then we get 2 peaks, and you keep doing it, the number of peaks grows exponentially. You keep duplicating and shrinking this function every single time. Okay, so again, the punchline is k compositions of this thing give you 2 to the k bumps. So the idea is that you hand me any basis you want, then what I'm just going to do is, with very little effort, construct this super bumpy function that your base is going to have to choke. So if you tell me, I believe in Fourier transforms, with sinusoids up to 1024 oscillations, yeah, no problem. I'll just stick 20 in the exponent here. Okay. So sorry, I'm just doing a little time calibration. So here's what we can prove with this. Something I did a couple years ago. It was essentially concurrent with the Elgamal result, and yeah, it was really funny. We ran into each other. At I guess based on the year, I'm not sure what they call the conference anymore, but we ran into each other, and it was like, hey, so what did you prove? And then it was like, oh, okay. You proved shallow, I proved deep, okay. But okay, so you give me an integer. The way this theorem works is like this. You give me an integer. You say, I believe in depth k. I've used PyTorch all my life. Depth 100 is the best thing ever. I construct a network with k-squared layers and k-squared nodes. I use that triangle mapping, the tent map. And you can't approximate it. So in other words, again, the game goes like this. You tell me you believe in k layers. I say, bad news. If your size is less than exponential, then you can't approximate anything that has k-squared layers. Okay, so just a few comments on this proof. So here's how the proof goes. So step 1 is this intuitive claim that if I have a highly oscillatory function, it cannot be approximated by a few oscillation function. Okay, so that's the intuitive claim. That's part of the proof. So there are 3 components of the proof. That's one of them. Another component of the proof is to say there exists such an oscillatory function. We already know that. We just constructed it. And another part of the theorem is to say that with a shallow network, we can't hope to have a function with few oscillations. And there are many reproofs of this. I proved it in the Univariate case because it's just some simple counting argument. I think one of my favorite versions of the proof is essentially in here. this paper proves the VC dimension of polynomials in 1968 in the West. And it cites, yeah, okay, let's not go into it, but. And then I was creepily stalking Vladimir Arnold on YouTube by using his Cyrillic name. And I skimmed to a random point in a video, and I saw him doing this counting argument on a chalkboard. So some reference to Vladimir Arnold. There's also this paper by Montefort, Pascanu, Cho, and Bengio, which was studying all the different arrangements you can get with these ReLU networks. It also had this counting argument. And then me and my student Bolton, who I mentioned briefly, we also included a version of it. It's essentially a VC dimension argument. So because of that, I will not prove this. I will point out this. So our goal is to say that a function with few oscillations cannot approximate a function with many oscillations. Every time I sat down to prove it, my proof was complicated. So maybe it's fun to just think for a second. It's an intuitive claim, but so here's how I proved it. I said, OK, well, first problem is that if I have my high oscillatory F and my low oscillatory G, this is actually not enough. So I've drawn the L1 norm here between them. If F has many oscillations, but they're scrunched up, I can't prove this high gap. OK, so I need F to have very kind of balanced oscillations. So that's why this word regular was appearing earlier that I didn't mention. OK, so we have a function with these regularly spaced oscillations, and I want to show that something with few oscillations can approximate it. I should say that this relates to the fact that my goal, I was stating my goal as being the L1 norm lower bound. But many people are happy with L infinity lower bounds, in which case this argument would have been fine. OK, so here's one way to do the argument. What you do is you isolate one oscillation of G, and with very few exceptions, you use an averaging argument in the proof, most of these large oscillations in G will hit many small oscillations in F, and there are so many of these oscillations in F that all I have to do is pay attention to the ones on the other side of this line I've drawn. So again, the way the proof works is I isolate single oscillations of the few oscillation function, and in those places I just look at across the line 1/2 all the oscillation in the other direction by the highly oscillatory function. So this proof, it gets, I think I wrote the number, 1/32. That should be, it should be about a half. This only gets 1/32 due to various forms of laziness, one of them being that it doesn't bother with these regions. OK. So here's the punchlines from this part of the talk. So the punchlines are that there are radial functions that seem very simple, and two-layer networks are just two hidden layer, two ReLU layer networks are fine with them. But we need exponential complexity if we only have one ReLU layer. Those are the results by Eldon Shamir and by Amit Danieli. Sorry, Ronen Eldon, Ohad Shamir, Amit Danieli. And then we have this result of, for any depth k, comparing it to k squared. So here's some remarks. So this function is 2 to the k Lipschitz. And maybe I'll have time to mention it later, but I've been highlighting a lot of these constructions where they're Lipschitz and where they're not. I'm slowly believing less and less in high Lipschitz functions. So, because don't expect to get them at a PyTorch, basically. And maybe in the open problem session later, we can discuss many variants of all these questions. We can talk about, the ideal question would be if you give me a k-layer network, I give you an algorithm that determines whether we should add another layer or not. Right? This is the question everybody wants to know. I ran PyTorch on ResNet 100. Should I do ResNet 101? I wish I could tell you. And another thing I should say is that all of these constructions were constructions. They weren't claims that you run into these things with gradient descent. They weren't claims that CFAR with SGD with whatever SVRG is running into them or something. OK, any questions so far?
I have a quick question. So
Yeah.
these constructions, is it considered that each neuron itself has a different, I guess it was one of your questions, each neuron itself is a different nonlinearity.
Oh,
So not in the depth, in the width.
yeah. Interestingly, in many of the proofs, it actually doesn't matter if you use a different nonlinearity for every single one. So I just happened to read that sentence last night in Eldon Shamir's proof. And in all of my proofs, it also doesn't matter. In Ahmed's proof, I don't remember, but in a lot of them, it doesn't matter.
So could you give some intuition why that doesn't matter?
Oh, yeah, sure. It's basically just the fact that they're all just easily convertible with each other. Like you give me that's why I'm talking about ReLU. I should have mentioned this. That's why I'm talking about ReLUs for most of this talk. You give me whatever activation you care about, I'll just use a bunch of ReLUs to approximate it.
But then you need to add depth, right?
No, actually, you can do this within a layer. You pay like a 1 over epsilon type thing.
I see.
I mean, that's still bad, but it's not a completely satisfying answer. I mean, the reason I'm doubling down on the ReLU is because ReLU has all these magical properties like positive homogeneity. But I guess to summarize the question is, for just like stating these existence type theorems, because of these types of things, it doesn't really matter. But maybe for some refined questions, it matters. Yeah?
So you mentioned that using less oscillatory function to approximate highly oscillatory. Isn't that people have been doing wavelets, doing what Fourier transform is trying to do? I mean, you use a lower frequency to approximate higher frequency. I mean, there's a fundamental limits there, right?
Sure.
Is that similarity there?
Yeah, there's a similarity there. Yeah. I mean, what I guess I'm saying here is that actually, interestingly, in this there's some old monograph by LeCun and Bengio where they actually, this was before any of these proofs happened, where they state that a good evidence of the power of depth is approximating Fourier transforms. If you think about the butterfly network that we use to compute Fourier transforms, it also has. Yeah, the way I would say it is that if you give me a fixed basis of some size, it has some maximum frequency, and I can quickly beat that frequency with a deep network. But I'm also cheating, right? I'm getting to pick my architecture. So, yeah, it's a good question. Okay. Let me do it this way. So let me try to be clean for the first time in 75 minutes, or sorry, 65. So let me tell you somewhat cleanly what this result is all about. So I've told you that I answered this question earlier that we can do multiplication. And I will just tell you the punchline for this construction. You can look at it in the slides in detail or in the paper I'll cite. This is not mine. So x squared is one of these functions that we can get epsilon close with log 1 over epsilon depth, log 1 over epsilon width. And the proof of this is like a trick proof. If you form the piecewise affine interpolations, subtract them from each other, you get these tent maps. You add the tent maps together, then you get the result. So here's the bound. You can take these triangles I told you about, add a bunch of them together, and you get x squared. And it's epsilon close with complexity log 1 over epsilon. And this gives us multiplication. Okay, we have multiplication, we have squaring, we've got polynomials. Okay, so anything you can write with a polynomial, we can approximate well. What I want to tell you about in this section of the talk is going one step beyond just polynomials, which is things with locally good Taylor expansions. So, we take a Taylor expansion, it drifts after a while, so I can't just replace a function with, I'm not just talking about replacing a function with a polynomial, I'm replacing it locally with a polynomial. So here's the theorem, and I'll just give you some highlights from it. So if you give me a d-dimensional function, and I say it has smoothness order R, people that know the lingo, I actually don't, I just basically picked it up. This is called the Sobolev ball. There are many different Sobolev balls with many different norms. This version of the Sobolev ball is just saying that all the derivatives up to R, all the partials up to degree R are bounded by 1. Okay, give me this function with all these smoothness conditions. Then there exists a network with essentially log 1 over epsilon. It's so hard to read. It's E. I was trying to be tricky. It's log 1 over epsilon, log 1 over epsilon over here. So the depth is log 1 over epsilon. That's necessary in this construction. But we're not caring about the magnitude of the weight. So that's log 1 over epsilon is necessary. And the width scales like 1 over epsilon, but it gets very good with the smoothness order. Okay, so this was proved by Urbana-Champaign in 2016, and a bunch of other people around the same time, and then after that I'll mention the references in just a second. But this is the proof that I've gone through in detail. That's why I'm presenting it. Okay, So this proof is pretty cool. What it does is it takes the function, computes all these Taylor expansions everywhere. So you get these little local polynomials, and then it multiplies them by bumps. Okay, so I've got my function f. I want to approximate it here by a polynomial, and I multiply it by a bump like this. I compute the polynomial, and then I multiply it by this bump. Why is that interesting? Polynomials themselves can't approximate bumps with low degree. So this construction is kind of non-polynomial, even though it's using polynomials. Okay, so that's how the proof works. And just a few quick comments. The Lipschitz constant, according to me, is kind of bad. Like I said, later I'll mention why that big Lipschitz constants scare me. I'll also say that to some extent, this result is actually a basis expansion. The only part of the construction that depends on f are these coefficients on these bump times polynomials. So it's still not using depth as much as it could in some sense. Though there is another related result in the paper. Here's some other results I should mention. So around the same time, Safran and Shamir also proved this. They did not use the x-squared construction I just told you about. They used a related one that did digit extraction, but it actually has a similar Lipschitz constant. So that applies there. And I checked all these other proofs out of paranoia. They all have the same Lipschitz constants internally. If you're curious about the other Sobolev norms, then that's what you can check in these other papers.
How explicit are the constant CDR and how big they are?
Oh yeah, I'm pretty nervous about those. He was pretty careful in that paper. Yeah, sorry, I don't know off the top of my head. It's like rude for me to say that I'm nervous about them. I'm nervous about them. I should check them. But probably controlled it.
Are these constructive proofs? Did I construct these layers if I want them?
Yeah, let me hand it to you. So they're completely constructive, and in fact, like I said, you only need, for a new function f, you only need to compute these multiplication coefficients, and the base is already lying around. Yeah, it's a completely constructive proof. This paper writes this proof out very nicely, and it talks about partitions of unity, and has little pictures, and lower bounds too, and yeah, it's a great paper. Oh, sorry, there was a one-word answer to that question. Constructive. Okay. Okay, so I wanted to say there. So let me just take 5 minutes to grab bag some things, and then well, maybe I should take 2 minutes to grab bag things so we have enough time for questions, right? More reasonable. Let me just answer these questions. The answer is no. There's an upper bound on how many pieces we can have. If I perturb these, add them to themselves a bunch of times, I'm going to exceed the upper bound on how many pieces this architecture can have. This is actually false, not closed under addition. But I kind of tricked you maybe. I said fixed architecture. Maybe the word fixed, I didn't even define it, right? RNNs simulate Turing machines? Yes, they can. You use F to model the state transition table, and you encode the tape in a single real number. But it's not easy. For a fact, I'll tell you later, just for people that don't know this, people that have been around me for more than 5 minutes, I keep repeating this, the step function is not a computable function. So yeah, this function, x maps to 1 if x is greater than or equal to 0, 0 if x less than, not computable. You have to read infinitely many bits. So to do digit extraction on this state is non-trivial. Okay. This is a cool result. It's true, you can do this. It's the Kolmogorov-Arnold theorem, it's from 56. And the proof is really intimidating. It's just a bunch of limits. And it constructs these fractal bases. The slides have this very offensively short sketch of the proof. But the activations have like high fractal dimension and stuff, so it's you're not going to plug, this you will not plug into PyTorch, yeah?
For the first question, maybe you addressed this already, and I missed it, and then I apologize. But if you were to consider infinite width networks with, say, bounded norm, does that answer change?
Okay, infinite width, you're fine. Bounded norm. The answer...
Well, I just want to make it bounded norm because maybe you can use a crazy set of infinite weights and make that not work.
So, I think this is a question, so I'm not just like taking offline to know the answer. I think this is a question that the answer will depend a lot on the exact the exact way we set it up. So there, if I like add and normalize, then I think we're maybe fine. But if I can add and not normalize, then I can get all sorts of crazy stuff. And yeah, so I think based on we have all summer, right? We can talk about it. But based on the explicit version of it, the answer might change. Yeah.
So just for number 2, I think if you want to extract L bits, you need L layers. So if you fix the depth, you can't do this to more than fixed precision.
Yeah.
Okay, I
Yeah.
misunderstood what you were.
Yeah. Oh, maybe I should
So
say.
each F needs to have a sort of arbitrary depth.
Yeah, this thing is, it takes many steps to do this on rolling. Yeah. Maybe I should have pointed out that there's actually another whole set of the talk. But so let me just pick one thing from here that's interesting. The sampling thing. I did not explain how the sampling works. This is super cool. The original reference, thanks to my friend Maxim Roginsky, is Kuran Gurvitz. There was a recent paper by Sim Gilbert Tuari, and then I use a version of this that's related to. If you just write down Rademacher complexity bound, and you just kind of confuse yourself that you switch X and A, you convert the Rademacher generalization bound into a uniform norm bound on the inputs. So we can use. So what does this tell us? It tells us the probability 1 minus 1 over epsilon, 1 over E. I only need constant probability. I'm just saying there exists one of these things. Okay, so I can use generalization bounds to guarantee that sampling from these infinite width networks gives us something cool. Again, these slides will be posted. Is Alexander here? I'm scared to say anything about it. Okay, I was just going to say really quickly that I keep talking about the Lipschitz constant. To some extent, Lipschitz constant high means you have adversarial examples, but it's not so simple. If you have examples far apart, you kind of want to be flat there. So there's some aspects of adversarial examples and adversarial stability that change a lot of the nature of these representation questions. And I think it'd be really exciting if people started working on things like representation questions related to adversarial stability. Sorry, that was so vague. Let me just see if there was something else I skipped that I wanted to include. Another representation thing that's pretty interesting is for generative networks, very simple things, like you have a uniform distribution, you split it up into two uniform distributions over disjoint sets. That's discontinuous. So a lot of these kind of mappings people are very comfortable with in GANs and VAEs are actually kind of very, very badly behaved, and maybe it has something to do with some aspects of the training that are difficult. Let me also say that I was very shocked reading these papers. It just came out of left field for me. These papers that give some convergence results for gradient descent on deep networks, they have representation results inside of them. And one of them says, they just give me this wide network. You take a tiny perturbation, you get any function you want. So there are all sorts of new representation questions that can be investigated based on this. Okay, I think I should stop for questions with that. Thanks.
More questions? Good, so let's break for lunch. We meet at 2. At 2, yeah. It's your lecture.